Hello everyone, I am Dr.VRAO-PHYSICAL. We have been learning or we have been discussing the chapter chemical equilibrium, and from the lecture 30 we came to know that equilibrium established in reversible reactions carried out in a closed vessel, and moreover we can apply law of mass action to equilibrium, right. So, let us consider a general reversible reaction, that is A moles of A, B moles of B gives rise to C moles of C and D moles of D. This is the reversible reaction, and in this reversible reaction there exists a equilibrium if this reaction is carried out in a closed vessel, right. So, for this reaction we can apply law of mass action, right. Already I told you the law of mass action, the rate at which a reaction proceeds is directly proportional to the product of active concentrations of the reactants, right. So, for this reaction we can apply law of mass action. Okay. So, law of mass action, for example, this is a reversible reaction, and in this two reactions takes place, that is A moles of A, B moles of B gives rise to C moles of C and D moles of D. This is called forward reaction, and the rate of this forward reaction is, according to law of mass action, rate of forward reaction is directly proportional to active concentration of reactants, that is A power A and B power B, and rate is equal to some constant K. When we remove the proportionality, we can write the proportionality constant. The proportionality constant for the forward reaction is Kf into K A power A and B power B. So, we applied the law of mass action to forward reaction, and we have another reaction, that is backward reaction. C moles of Z, D moles of D reacts to form A moles of A plus B moles of B. This is backward reaction. You can observe this. This is the backward reaction from right to left. From left to right is called forward reaction, and right to left is backward reaction. Okay, this is the backward reaction, and for this reaction we can apply rate is directly proportional to concentration C power C and concentration of D power D. And if we remove the proportionality, rate is equal to some constant. This constant for the backward reaction is taken as a Kb into concentration C power C and concentration D power D. Okay. Already I told you, in reversible reaction there is tug of war has been takes place. There is a tug of war has been takes place, as like in the tug of war game. In the tug of war game, one group is pulling in one side and another group is pulling in another side, and at a certain time the two groups are pulling with equal energy, and there exists a equilibrium. Whenever the energies of two groups are equal, there exists a equilibrium. Therefore, in the same manner, in the reversible reactions, tug of war has been takes place, and at equilibrium the rate of forward reaction is equal to rate of backward reaction, as like in the tug of war game, right. So, rate of forward reaction, the rate of forward reaction is this Kf into concentration A power A and concentration B power B is equal to rate of backward reaction, that is Kb is into C power C and D power D. Alright. So, let us take the ratio of this Kf forward reaction to backward reaction. Let us take the ratio Kf by Kp, then concentration C power C and concentration D power D by concentration A power A into concentration B power B. So, we take the ratio of forward reaction to backward reaction, and this ratio, we can write this ratio as constant, that is that constant is K. K is equal to concentration C power C concentration D power D by concentration A power A by concentration B power B, right. If these concentrations are expressed in molar concentrations, if that concentration of the products and equilibrium constant is a ratio of concentration of products to concentration of reactants. If these concentrations are expressed in moles per liter, then the equilibrium constant K can be written as Kc. K can be written as Kc. So, if these concentrations are molar concentrations, then we can write the subscript C for K. Then it is called Kc. Kc, that means equilibrium concentrations are expressed in moles per liter, right. For example, if the reaction takes place, molar concentrations are the concentrations that is the customary unit to express the concentration of solutions, that is the moles per liter is the unit, and that unit is customary to apply for solutions. Okay, but not all the reactions, takes place in solutions. Reactions takes place between gases. What happens and how can we represent the equilibrium constant if the reaction takes place between gases? If the reaction takes place between solutions, we can write the concentration of products by concentration of products and concentration of reactants in moles per liter. But how can we represent the equilibrium constant if the reaction takes place in gases? So, for example, if the reaction takes place between, let us consider the gaseous reaction, that is PCl5 gas gives rise to PCl3 gas plus Cl2 gas. This is the gaseous reaction because all the reactants and products are in the gaseous phase, and we can also we can say that the equilibrium established in this reversible reaction is called homogeneous equilibrium, because all the reactants and products are in the same phase, right. So, for this reaction PCl5 gives rise to PCl3 and plus Cl2 gas. This is a gaseous reaction. How can we represent the equilibrium constant for this reaction? First, you should know one thing, that already I told you in the lecture 30. Okay, equilibrium concentrations are expressed in activities, that is activity is equal to actual concentration into activity coefficient. For solutions, for solutions. This is for solutions. In solutions, C is expressed in moles per liter, moles per liter. And for gases, activity is equal to pressure into activity coefficient, partial pressure into activity coefficient for gases. For gases. For gases, how can we express the concentration of the gases? With partial pressures, right? And one more thing is that already I told you in the lecture 30, the activity coefficient for dilute solutions and gases is equal to 1. The activity coefficient for dilute solutions, and gases, gamma is equal to 1. Activity coefficient becomes 1. So, for dilute solutions, A becomes C, and for gases, A is equal to P, because coefficient gamma is equal to 1. Gamma is equal to 1. There is no activity. Okay, so gamma equal to G. So, A equal to P, activity is equal to pressure in case of gaseous reactions, and activity is equal to molar concentration if the reaction takes place in solutions. Now, let us apply this activity for this reversible reaction. Let us express the activities, let us express the concentrations. Already I told you equilibrium constant, we can write the equilibrium constant as a concentration of products by concentration of reactants. So, concentration of products, we are expressing the concentration in activities. A PCl3 gas, okay, A PCl3, A activity of Cl2 by activity of PCl5, activity of PCl5, right, activity of PCl5. But activity is equal to, in gaseous reactions, activity is equal to pressure. Activity is equal to pressure. Already I told you, just now I told you, activity is equal to pressure for gaseous reactions, right? So, activity is equal to P. So, we can write that partial pressure of PCl3 and partial pressure of Cl2 gas by partial pressure of PCl5. So, when we express the concentrations in partial pressures, then we can write the equilibrium constant, we can write the subscript for K, that is Kp, that is Kp. So, there is much difference exists between Kc and Kp. Kc is the equilibrium constant for the reactions takes place in solutions, right, and Kp is the equilibrium constant that existed for the gaseous reactions. Let us see some more examples. Let us see some more examples, that is (2SO2) gas plus O2 gives rise to 2SO3. 2SO3. Okay. So, this is also a gaseous reaction. This is the gas and this is a gas and this is a gas, right. So, we can write the equilibrium constant Kp. We can write the gases equilibrium constant Kp. So, partial pressure, equilibrium constant is a ratio of concentration of products to concentration of reactants, but here the reactants and products are gases. So, we can express the concentration of gases in partial pressure. So, partial pressure of SO3 square, alright, and partial pressure of SO2 square and partial pressure of O2. So, this is the way to represent the equilibrium constant, to write the equilibrium constant for the reactions between the gases, for the reactions in gaseous phase, right. So, Kp is equal to partial pressure of SO3 and partial pressure of SO2 and partial pressure of O2. Okay, let us consider another example, that is, let us consider the another example. CaCO3 is a solid and it decomposes to form calcium oxide, which is a solid, and CO2, which is a gas. Okay. So, the equilibrium, here the reactant is solid and product is, one of the product is solid and another one of the product is gas. So, this is in this reaction, reactants are in the solid phase and some products are in the solid state and one product is in the gaseous phase. So, the equilibrium exists in this reversible reaction, the equilibrium exists in this reversible reaction is heterogeneous equilibrium. It is heterogeneous equilibrium because reactants and products are in different phases, right. So, we can write the equilibrium constant for this, whatever the phase of the reactants and products, write the equilibrium constant in activities. Okay, let us write the equilibrium constant in activities. Okay, so activity of calcium oxide. So equilibrium constant is the ratio of products to reactants. Okay, activity of calcium oxide and the activity of CO2 gas and activity of CaCO3, activity of CaCO3. Already I told you for solids and pure liquids, activity is equal to 1, because in solids and pure liquids there is no movement of ions. So, activity is equal to 1, activity is equal to 1. So, we can write activity K is equal to activity of calcium oxide, it is a solid, so its activity equal to 1, activity of CO2 gas, but its activity not equal to 1, right, and activity of CaCO3, it is a solid, so its activity also equal to 1. So, that remains activity of CO2, activity of CO2. So, this is the equilibrium constant in activities Ka. So, activity of CO2, but for gases activity coefficient is equal to 1 for dilute solutions, and for gases activity coefficient, we know that activity is equal to actual concentration into a partial pressure into activity coefficient. For gases activity coefficient is equal to 1, then activity is equal to pressure. Okay, this is the very important point that you should keep in your mind. Whatever the reaction phase is, whatever the equilibrium is, whether it is homogeneous equilibrium or heterogeneous equilibrium, write the equilibrium constant in activities. Write the equilibrium constant in activities, then you can convert into Kp or Kc. You can convert that equilibrium constant based on the convenience and based on the phases of the reactants and products. If all the reactants or products are in the gaseous phase, then we can write the Kp. Some are in solid phase and some are liquid phase, then it is better to write the equilibrium constant in activities. Then you can convert that into Ka or Kp based on the convenience, right. So, activity is equal to pressure. For gases CO2 is a gas, so activity is equal to pressure into activity coefficient, and for gases activity coefficient is equal to 1 and activity is equal to pressure. So, we can write it as a partial pressure of CO2 and it becomes Kc. Kc is equal to partial pressure of CO2, and that equilibrium constant is equal to Kc is equal to partial pressure of CO2. Okay, that is there are two equilibrium constants, that is Kc and Kp. Okay, this is the equilibrium constant in which the concentration of products and reactants are expressed in moles per liter, right, and this is the equilibrium constant where the products and reactant concentrations are expressed in partial pressures, right. One more equilibrium constant is also there, that is Kx, or sometimes it is represented it is read as xi. So, equilibrium constant also expressed in mole fractions, but it is not familiar or not familiar, but these two are very familiar, Kc and Kp. So, the relation between Kc and Kp is observed as by the equation Kc is equal to Kp into Kp is equal to Kc into Kp is equal to Kc into RT power delta n, RT power delta n, RT power delta n, RT power delta n. 1 minute. Okay. So, Kp is equal to Kc into RT power delta n. This is the relation between Kp and Kc, and where delta n is number of gaseous products, minus number of moles of gaseous products, number of moles of gaseous products minus number of moles of gaseous reactants, number of moles of gaseous reactants. So, delta n, we can get the delta n value from subtracting the number of moles of gaseous products minus number of moles of gaseous reactants. And one more relation that exists between Kp and Kx, is P power delta n, where delta n is also equal to number of moles of gaseous products minus number of moles of gaseous reactants. Now, coming to the units of Kp and Kc, okay, I shall write here, okay, Kp, units of Kp is equal to pressure units power delta n, and units for Kc is moles per liter whole power delta n, or we can write it as mole liter inverse power delta n, right. This is the units for by which this Kp is equal to units of pressure power whole power delta n. If delta n is equal to 0, and one more thing is that if delta n is equal to 0, Kp is equal to Kc. That is equilibrium constant expressed in partial pressures is equal to equilibrium constant expressed in molar concentrations. If delta n equal to 0, if delta n not equal to 0, then Kp is equal to pressure units whole power delta n, and Kc is equal to moles per and molar concentration units power whole power delta n, right. So, this is about equilibrium and equilibrium constant. Okay, one thing I want to conclude, that equilibrium established in reversible reactions carried out in a closed vessel, right, and we can apply law of mass action to equilibrium, whether it is homogeneous equilibrium or heterogeneous equilibrium. Okay, so there are two equilibrium constants Kp and Kc, and the relation between Kp and Kc is Kp is equal to Kc into RT power delta n, and there is another, and we can express the equilibrium constant in mole fractions also. Then we can write that equilibrium constant as Kx or Kxi. Okay, and the relation between Kp and Kx is equal to Kp is equal to Kx into P power delta n. Why then? Okay, so what by equilibrium constant, what we know? By the value of equilibrium constant, we came to know that equilibrium constant is a ratio of concentration of products concentration of products to concentration of reactants. Okay, equilibrium constant, we came to know that equilibrium constant is a ratio of concentration of products to concentration of reactants. So what does that equilibrium constant tells? What that equilibrium constant explains? Let us see what is the what that equilibrium constant explains. The value of equilibrium constant, let us see. Okay, so equilibrium constant K is equal to concentration C power C and concentration D power D by concentration of A power A and concentration of B power B. It is nothing but equilibrium constant is a ratio of products to concentration of products to concentration of reactants. Okay, so what this equilibrium constant tells? Okay, the value of equilibrium constant, when we substitute the concentration of products and concentration of reactants, we can get a value for equilibrium constant. What that equilibrium constant says? What that equilibrium constant concludes? Right, equilibrium constant, the value of equilibrium constant K is a measure of to what extent that reaction proceeds. I repeat, equilibrium constant is a measure of to what extent that reaction proceeds. To what extent that reaction proceeds, that can be measured, that can be known from equilibrium constant value, right? So if that equilibrium constant K is greater than or equal to 10 cube, then that reaction is a forward reaction. That reaction is forward reaction. That is products are predominant over reactants, because forward reaction is from left to right. That is products. Left to right means reactants to products. So if K value is greater than or equal to 10 cube, that indicates the forward reaction, that favors the shows the forward reaction is favors, that forward reaction takes place in greater extent. So forward reaction, so K greater than or equal to 10 cube, that indicates forward reaction. That means products are predominant over reactants, right? And if K is less than 10 power minus 3, if K is less than 10 power minus 3, if equilibrium constant K value is less than 10 power minus 3, that indicates a backward reaction. That indicates backward reaction. That means reactants are predominant over products, because backward reaction is product to reactants from right to left. Okay, what is left? Reactants are in the left side, so reactants are predominant over products. Okay, if K is 10 power minus 3 is less than k less than 10 power minus 3. If k is in between 10 in the range of 10 power 3 to 10 power minus 3, that indicates concentration of products and concentration of reactants are comparable. If if the equilibrium constant k is in the range of 10 cube to 10 power minus 3, that k value extending from that k value, if that k value is in between 10 power minus 3 and 10 cube, that indicates the concentration of reactants and products are comparable. But whereas here the forward reaction means here the products are predominant, here the reactants are predominant. But if k value is in between these two values, concentration of reactants and products are comparable. So, by the value of equilibrium constant, we came to know that we can know whether the forward reaction is predominant or the backward reaction is predominant, and we can know that whether the equilibrium exists in that reversible reaction or not. If k value is in between in these two values, that is 10 power 3 to 10 power minus 3, then there exists a equilibrium between reactants and products, right? And one more thing is that there is another concept called reaction quotient. What is called reaction quotient? Reaction quotient. Reaction quotient. One minute. Reaction quotient. Okay, so reaction quotient Q. So Q reaction quotient is also defined as like equilibrium constant, as like equilibrium constant. For example, if you take a reaction 2A gives rise to C plus D, 2A gives rise to C plus D, we can write the reaction quotient for this reaction. So as like equilibrium constant, Q is equal to concentration of C power concentration of D by concentration of A power 2. So reaction quotient is defined as equilibrium constant. Equilibrium constant, how can we define the equilibrium constant? Equilibrium constant K is ratio of products to concentration of, it is equilibrium constant is a ratio of concentration of products to concentration of reactants. So reaction quotient is also defined as equilibrium constant. So Q is also a Q is equal to concentration of products by concentration of reactants. But what is the necessary condition? What is the such that condition in reaction quotient is the concentrations here, the concentrations are need not be equilibrium concentrations, but in equilibrium constant these concentrations should be equilibrium concentrations, but in reaction quotient these the concentrations are need not be equilibrium concentrations. And from the, if Q is QC, for example, if this expressed in molar concentration, then we can write it as QC. QC is equal to Kc. Then equilibrium, that shows equilibrium, that indicates equilibrium. If QC is greater than Kc, that indicates backward reaction, that indicates backward reaction, and if QC is less than Kc, that indicates forward reaction, forward reaction. Okay, if QC is greater than KC, that indicates backward reaction. Backward reaction means from right to left, reactants are predominant over products, and if QC is less than KC, that indicates forward reaction, that is products are predominant than over reactants. If QC is equal to KC, that indicates equilibrium, that indicates equilibrium. So this is all about equilibrium constant, equilibrium and equilibrium constant. One thing that you should keep in your mind is that in reversible reaction there is a tug of war takes place between reactants and products. In the tug of war game, one group pulling with equal force and another group is also pulling with the same force. When these forces are becomes equal, that tug, that is that there exists a equilibrium between these two groups. In the same manner, if the rate of forward and backward reactions are equal, there exists a equilibrium. That is, at equilibrium, the rate of forward reaction and backward reactions are equal, right? So this is about equilibrium and equilibrium constant. In the next video, we shall go through the factors affecting equilibrium constant. Okay, thank you.